Okay, so the next section we're going to look at is the last chapter of the course with galactic evolution and formation. Okay, so if we start this, so galaxy formation and evolution. Okay, so we're going to look at first of all some of the observational methods that we use to look at the really early history of galaxy formation, and then we'll use some of that to kind of build a general framework which is consistent with all the observational data for how we think galaxies evolve from the early stages to what we see today. Okay, so obviously because C is finite, that means that distant galaxies tend to be earlier galaxies. Okay, fine. So what are we talking about? We're talking about a redshift of approximately 1. That corresponds to when the universe is about half the age it currently is. Universe half current universe age. So that's approximately equal to 7 billion years ago, given that the universe is about 14 billion years now. If you go to higher redshifts higher than or roughly equal to 6, we're talking about roughly 1 billion years after the Big Bang. Okay, so when we get to these really high redshifts, one of the challenges that astrophysicists face is that the luminosities of the galaxies becomes extremely faint. It's hard to see them directly using just optical telescopes. So we have to work out some indirect ways of finding these objects. So the methods we're talking about, you can just do some direct observation, but this becomes tricky because high redshift equals faint. That's not how you spell faint. Equals faint galaxies. Okay, so you can do some direct stuff, but it's hard. So what are some indirect ways of doing it? Method 2. So what we do in this case is that we do observations in several bands. At least 6. Remember, we cut up the EM spectrum into these different bands, and when you're doing astrophysics observations, you're normally only looking at maybe a few of these bands at a time. But if we combine several bands, at least 6 of them, then we can basically use some simple models for galaxy formation, what light we expect, IMFs, things like that, which we discussed previously, to work out what would be the best type of galaxy and at what redshift to produce the observed data across multiple bands. So at least 6, then we model. What type of galaxy and what redshift Z best fits all the data. Okay, so you can imagine it takes a lot longer to get this data because you have to examine the same patch of the sky using multiple filters, but once you've got that extra data, you can do this kind of analysis. And actually, in terms of modeling the redshift, we think the errors are quite small on this. The errors on the redshift give a delta Z of less than 0.1, which is a pretty good estimate for the errors on the redshift. What do we see when we employ this method? Well, first of all, we see galaxies up to quite a high redshift of around 5.6, although most galaxies are within a Z of 0.5 to 2. We also notice that there is a change. Above a redshift of around 1.5, we see a change. We see fewer spirals and mainly irregular galaxies. Remember, the morphologies of galaxies today, broadly speaking, are spirals and ellipticals, and then there was a smaller set of irregulars, which didn't really talk about previously. Irregulars are just exactly what they sound like. The shapes are not going to be nice patterns, essentially. Right? You're not going to get the nice ovoid shapes of ellipticals or the nice spiral shapes of spirals. There could be all kinds of misshapen oddities. And we see mainly irregulars after a particular redshift of around 1.5. Okay, so that comes from directly looking at these different bands and combining them together. Another method, method 3, dropouts. So basically, in order to look at this, what we do is we look for a very particular type of line, and given the fact that that particular emission line that we're looking for is going to be redshifted by a certain amount at these high redshifts, we can begin to look for these indicators of star formation, even in areas where we don't see objects that could be the source of the star formation. So we look for Lyman alpha lines indicating star formation even if object producing the line cannot be seen. So basically we see something called the Lyman break. Okay, so what is the Lyman break? This is a drop-off in the spectrum after 91.2 nanometers in the rest frame of the object. The shorter wavelengths, so the wavelengths which are smaller than 91.2 nanometers, shorter wavelengths are removed from the spectrum. By photoionization. Photoionization of hydrogen. So prior to this very sharp break at the 91.2 nanometer line, we've got a fairly flat spectrum. So basically the galaxies are producing all the frequencies of light from the UV range all the way up to optical, and then after that, when you get to smaller wavelengths in the optical range, there's a sharp drop off, and that's caused by the fact that at those higher wavelengths, at those shorter wavelengths, we're going to get the photoionization of any hydrogen they encounter, so that absorbs the light, and so we don't see that anymore. So prior to the break, a fairly flat spectrum. UV to optical. Okay, so why would that be the case? What would cause there to be a fairly flat spectrum from UV to optical? We'd expect that to be caused by the presence of a large number of young massive stars. Lots of young massive stars producing lots of light in this range. Okay, then we get this break at 91.2 nanometer point, and after that you get a sharp drop off in the amount of light being received. What we observe, however, is that it's not going to be at the 91.2 nanometer range, because the redshift of the galaxy will shift that drop-off point to a different band in terms of what we observe. So in terms of observation, at a redshift of around 3, the drop-off is shifted to the U band. At higher Z, it goes through the blue band, the violet band, the red band, and for really high redshifts, so redshifts greater than 5.6, we have to use the infrared band to look for the drop-off. Okay, but once you see the drop-off, you've got a strong indication that there is this particular type of galaxy where you get a large number of young massive stars, but because of the presence of hydrogen, you get a nice flat spectrum from UV to optical and then a drop-off at the Lyman break. So once you see that drop-off, you know there's probably going to be a galaxy there with the kind of properties that we just described. Okay, so then we can use the observations to start to work out the numbers of these galaxies and how they cluster in the nearby region. So these Lyman break galaxies their density and clustering suggest they are the ancestors of elliptical galaxies. Of ellipticals. They tend to be smaller, with a half-light radius of less than or equal to 3 kiloparsecs. Okay, so they're fairly small compared to modern galaxies. Okay. What else? How else are we going to find these really early type galaxies? Another method we can use is to look for the Lyman alpha lines directly. From star formation. So this is different to the Lyman break we were talking about previously. The Lyman alpha line is a particular spectral line associated with star formation. And we can sometimes see this particular line even if we can't see at all the background spectrum against which the line exists. So normally you'd have your spectrum like this, you'd have wavelength, intensity, and you'd have some kind of black body distribution, and against this there'd also be peaks where you get these transition lines, right? You get certain peaks at certain points representing the different elements. It'd be much more complicated than the diagram I've just drawn here, but you get the idea. As you get to higher and higher redshifts, the intensity of that black body spectrum is going to decrease because the objects become too faint. But sometimes we can still see the peaks of the spectral lines, even if you can't see the black body distribution behind it all. And by looking for particularly the Lyman alpha line, which is a particular line for hydrogen, we can then surmise that there's an object there undergoing star formation, even if we can't see any more details. So the continuum may be too faint, but can see Lyman alpha line. And when you do see it, it indicates star formation is occurring. But crucially, not all galaxies which are producing stars will have high Lyman alpha lines being produced as well. So star formation galaxies don't always produce this line. Why? Because dust can obscure it. Dust absorbs the line. Okay, so the absence of the line doesn't indicate that star formation is not happening. So if dust is absorbing the Lyman alpha line, sometimes what we can look at is the re-emission of the light by the dust. And we know that the dust tends to re-emit in the sub-millimeter range. So we can look for dust emission also. Lyman alpha is re-emitted by dust and then redshifted redshifted to the sub-millimeter range. Okay, and then we can look for this signal, and that will allow us to work out whether there are these star formation galaxies nearby. So using this method, we find at z greater than or roughly equal to 2 a population of star-forming galaxies. When we analyze those galaxies that we found using this method, they tend to be ellipticals in a star-forming period. And by star-forming period, I mean they are really going for it. Their star formation rates are really high. So star formation rate of approximately 1,000 solar masses per year. So if you compare this to some of the numbers that we had previously for star formation rates, this is considerably higher. So this is very high. But these are also very dusty galaxies, so hard to see. So you have to rely on this indirect dust emission. Okay, cool. So that's some information about how we do the observations at these really high redshifts if you want to look at the early galaxies which first formed in the universe. Using a comparison between the types of galaxies we see in the really early universe with the types of galaxies we see today, we want to kind of bridge the two and see if we can come up with a model which will allow us to see how the galaxies have evolved as the universe has aged. So that's the last section of the course. We're going to talk about some very basic evolution models. Okay, so there are three components to evolution models. Move this up slightly. There's the star formation history of a galaxy. There is the fading and reddening of the stellar population. And finally, there are mergers. Okay, these are the three components that have to go into any model of galaxy evolution. And on the basis of these three components, this all comes from observations of things like color, metallicity, luminosity, mass functions, etc. Okay, so using those observations, we can build our model in these three factors. So what's a brief overview of the kind of the main standard picture of how galaxies evolved. The earliest period in the universe would have seen density perturbations. Density perturbations in the early universe mainly it would have been dark matter we talked about this previously, but in order to achieve the kind of star formation and galaxy formation at the right time period in the history of the universe, we need to have the seeds of galaxies forming at a time when normal, ordinary baryonic matter would have been too hot to actually begin collapse. So if you imagine you had a universe just full of baryonic matter and there's a small density perturbation in one region, that density perturbation then undergoes gravitational attraction for all the material nearby, and it starts to then pull in more matter, becoming more dense, and there's a snowball effect. However, if the universe is sufficiently hot, as the density perturbation begins to grow, it gets hotter, and the thermal energy could be enough to counteract the inward pull of gravity, and so those density perturbations may not get a chance to begin that snowball. But with dark matter, that doesn't happen. The dark matter density perturbations start to grow almost as soon as they're formed. Because they don't interact with light, they have no thermal energy. So their gravitational potentials can just grow and grow and grow and grow. So that's what happens in the early universe. You have this distribution of dark matter and baryons. The dark matter is able to start to cluster and form small gravitational potential wells early, and there's nothing to stop those gravitational potential wells growing, and then the baryonic matter just follows the gravitational potential left by those early perturbations in the dark matter density. Okay, baryons then fall into those wells, but baryons, unlike dark matter, baryons can interact with each other quite significantly. Baryons, however, will interact via via shocks and etc. Shock waves in the baryon fluid. And so what this produces is that you get at the end baryon dominated centers to these gravitational potential wells. To the potential wells. And we get, basically at the end of the process, we get the first proto-galaxies being formed. So we have the formation of proto-galaxies. Okay, cool. So once we've got our proto-galaxies, what's the next stage? The next stage is going to be star formation. Star formation starts. The density is going to slowly be ramping up, and eventually it gets hot enough that you get the first stars being made. These are the population 3 stars. If you remember in the earlier parts of the course, we talked about how the generations are labelled. Stars today are called population 1. The first stars to form are called population 3. We don't have any population 3 stars that we can directly observe today, but they're expected to be. Metal-free. Okay, so there are no heavy elements because all the heavier elements need supernovas or the kind of very massive stars that undergo up to iron. They can start to fuse them, or supernovas to form even heavier elements. Since those events haven't happened yet, the earliest stars will be metal-free. We also expect them to be much more massive than modern stars. We're talking order hundreds of solar masses. And what that means is you have short lifetimes. The more massive a star is, the shorter they live. Short lifetimes. And at the end of their lives, the population 3 stars, they leave their metals then for population 2 stars to begin their journeys. So leave metals in the ISM for population 2 after they die. Fine. So we've got now these small galaxies, they've got stars in them. We're also going to then start seeing the proto-galaxies begin mergers. And obviously as they merge, their size is going to increase and you get these larger galaxies that we see today. You can get all sorts of other effects as well. Some of the gas inflow due to larger galaxies can start to feed and fuel the central supermassive black holes at the center of these proto-galaxies. Can fuel the black hole at the center and produce a quasar, which we talked about earlier in the course. These active galactic nuclei where the supermassive black holes are kind of bringing in all the material. Okay. The accretion disk around the black hole will eventually form the spiral disk of spirals. Oh, sorry. Will eventually form the spiral disk of spiral galaxies. Great. 4. We note that the star formation rate per unit volume was roughly constant. From high Z to a Z of approximately 1. Okay, so in the early universe till today, star formation once it began was roughly constant from the early universe to redshift of 1, and then there's a sharp drop off. As the initial interstellar medium gets used up, there is less available for the next generation of stars. So most galaxies have undergone their primary period of star formation, and now they're in a lower star formation rate period. Last bit about mergers. We know that galaxies and clusters will evolve differently to those not. Okay, why is that going to be true? Well, there's a few different effects that galaxies and clusters have to face that those that are not in clusters don't. The most obvious being, you're more likely to have a merger. There are also going to be tidal effects. And even if there are no mergers and there are no significant tidal effects, just the gas in the galaxies will be drawn out and twisted around and maybe taken or dragged off the galaxies. So the gas can be stripped and dragged away. All of this is to say that the late time evolution of a galaxy is largely dependent upon its local environment. So unless you know the local environment, the galaxy is very difficult to say in general terms how the evolution of a galaxy will behave in the last 2 or 3 billion years. Prior to that, though, the story is a lot more regular and a lot more uniform for most galaxies. Okay, that is the last bit of the course. Good, so that completes the lecture series. I think the only thing left to do is problem class questions. My plan was that I was going to spend maybe a little bit of time talking about cosmology to fill in some of the last couple of lectures for the term, but I guess now that we're not having face-to-face lectures anymore, I'm not sure that would be the best idea. So my plan is to hopefully do some problem class questions with you soon. Okay, thanks very much, and that hopefully is the end of the lecture course.